Okay. Use. Okay. So yeah, I'm not seeing now Discord. So if you don't hear me well, please say to me like speaking, not do not type. Okay, so here I was saying that before getting into more details, I want to yeah, show this chemical review on protein allostery and conformational dynamics. And of course, you already, I mean, you know what is allostery, so you know that the function of many proteins is regulated thanks to this allosteric process. So in some cases, if you look at figure 1, what happens is that, yeah, so this gray area is a protein. So for substrate binding, in some cases, you need to have some effector binding. So, yeah, some effector binding. And this effector could be another molecule, another protein, etc. No? So there are different types of allosteric regulations. And also in this figure, they show that well, there are two types of allosteric regulation. Yeah, so if you look at figure 1b, so this allosteric binding may result in a change in the conformational state. So I don't know. So this binding so changes the conformation of the enzyme that now has a higher affinity for the substrate. And this change in conformation is shown by this shift in the free energy basing. Or you can also have this dynamically based allostery, where it's basically the free energy basing that gets altered, the how wide it is. And well, anyway, so there are different types of allosteric pathways and allosteric mechanisms that I'm not going to show, to talk about in this tutorial. But the idea is that in this, if we go to the next slide, so these allosteric systems or this allosteric communication has been studied by using NMR, but also by using molecular dynamic simulations. And yeah, I'm not going to explain about NMR, but we will focus on this section of the paper that is based on path and community analysis. So in this, in these studies where the allosteric communication is investigated, usually what is used is, well, they use concepts and methods from graph theory. And in this graph theory, there are two important properties of graphs that have been or that can be applied or have been applied in for studying different allosteric systems. One is the shortest path between two nodes, and another interesting property is the partitioning of this graph into communities. Okay, the idea is, okay, now there are multiple variations and many different studies that are using different variations for that, but I will just explain like the basics and so that we can follow what we do when we apply the shortest path map. So the first, well, here it's nice the chemical review because they do like the history, of the whole thing. So they start saying that, well, the first graph models that were used were based on looking at the X-ray structure, so the static. And basically, in the most simplified, the simplest version, they look at this X-ray structure and they say, okay, so we will draw a line between one residue and the other residue if those two residues are below a certain distance threshold. If they are, then we will assume these are connected, and we will draw a line between residue 1 and residue 2. Okay, so this is what the first models were doing. Then there were some refinements, further refinements on how to define which nodes should be connected or not. The major step was done by SETI and coworkers, where they define these contact maps, so these distances, based on molecular dynamic simulations. So they did these MDs, usually not that long MDs, and with these MDs, they applied the same concept. So they converted the protein into a graph. So each node here in A, each sphere denotes a different residue, and you draw a line between the different residues if these two residues have been less than whatever time. Well, in this case, I think they specified a cutoff for a specified fraction of the simulation time. So if they stay at less than 6 angstroms or 5 angstroms, more than 75% of the MD simulation time, they draw a line between these two different residues. Okay, and the other, what I think the most important thing that was introduced in this paper is that the path length, so the line that is drawn between residue 2 and residue 3, for example, the length of this line it depends on the covariance matrix or the normalized covariance matrix of the residue position. So you take into account the correlation between the movement of residue 2 and the movement of residue 3. And the length is like the logarithm of this correlation value. So, well, and here you say, well, how this covariance matrix is computed. Well, basically you check how residue 1 has been displaced from the mean position of this same residue, and how this displacement, whether this displacement of residue 1 and residue 2 are correlated or not correlated. So they have moved in a correlated manner or non-correlated manner. And the idea is that if you compute this correlation matrix, then you'll get values that move from 1, so they are correlated. Well, you can also get -1, but as you do so you change it to positive, then it will be, we can just focus on 1, so highly correlated. Doesn't matter if it's anti-correlated or correlated. When that is the case, then if you apply equation 17, what will happen is that the path length will be closer to 0, so shorter. However, if you have that the movement of residue 1 and residue 2 is uncorrelated, then this correlation value will be closer to 0, and so the length of the path will be super long. Okay, so with that, you can define this kind of path, this graph, that has basically a line between the different residues that have been less than whatever time during the MD simulation closed, less than whatever angstroms, and the line that will connect these different residues will be related to the correlation of these two residues. Yeah? And then once you have this plot, this graph, here you can see which is the shortest path between the different nodes of this graph. And here in the figure, it's represented, and you basically look at the values. For example, it's represented from 1 to 7, so it's 1.2, 0.8, 1. So these to go from 1 to 7. This is the shortest path. It's shorter than rather going from 1, 5, 5, 6, 6, 8, 8, whatever, 9, and 7. Yeah. So you can define this shortest path property. The point is that in these studies, the main focus was to, of course, compute this graph, but further analyze it and subtract here the communities, do the community analysis. And so the main focus always is to, most of the time is to check which are the communities, so whether my enzyme can be, now I'm in the next slide, whether there are some parts of the enzyme that can be considered communities that are that act as a whole. Let's say, the conformational dynamics of this part is like more like a block, and how these different communities are connected through the enzyme regions. And for that, they use this Girvan-Newman algorithm. So there are different, in graph theory, there are different algorithms that try to find communities in these original graphs. And in the particular case, in this study, in this particular case, they use the Girvan-Newman algorithm, which is based on the H-betweenness. And this H-betweenness is related to the number of shortest paths that cross a particular H. So if you look at now at figure B, you'll see that while this graph could be, the shape it has could be divided into two communities. One that, the green and the red communities, and there is the blue path that it's the one, or the most important edge that will separate these two different communities. So basically, by doing this algorithm and computing shortest path maps, they apply it to try to find these different communities, and they do it iteratively. And you see here also I put below some examples. So for example, eGPS that of course you are quite familiar with. And also here another one, PIN1. Also there have been in tryptophan synthase, there are some this kind of communities plots, and you see that in the communities plots you have how the different parts of the enzyme are correlated, the movement of different parts of the enzyme are correlated, and how these are connected. Okay, so mostly, and this kind of, this is interesting to analyze. And so the enzyme, for example, in the apostate, or once the effector is bound, and at different stages of the mechanism, let's say, of the allosteric mechanism. In these studies, and then there are other variations, like the correlation matrix, so could be another one. And for example, Ribalta proposed another approach, and there have been many other variations. But the idea in these allosteric studies is always to try to apply graph theory, and to find the communities, and how the connections between the different communities of the enzyme have been altered after effector binding. Okay, so now if we go to the next, then I'll like to go a little bit more into the detail about how this DINACOM works. The first is, so we have already seen, so the shortest, the concept, let's say, so we use covariance, so how much two variables change together. And here what we basically see, or what we do, is we compute how the C alpha or C beta or whatever position of the residue has been changed along the MD simulation with respect to the average structure, and how and how this and also and in this case you can also have positive, plus so greater values so the correlated or anti-correlated, no? So positive will means that one variable, so if you have higher values of one variable, will correspond to higher values of the other, and negative means that one is big, the other one is small, let's say. And this covariance can be, if you go to the next slide, if you divide it by the standard deviation, you have the Pearson coefficient. And here is when we say, the +1, -1, and 0. No, if +1. So when the movement of residue 1 is correlated to the movement of residue whatever. -1 if they are anti-correlated, and 0 if there is no correlation between the movement of these two residues. So with that, you can define the correlation matrix, and in this correlation matrix, you will have for each pair of residues this correlation value, this Pearson coefficient. And this matrix is the one that we use, that we need for computing the shortest path map. So now, if you go to the, so we will need, for computing the shortest path map, this correlation matrix that will give me information about these coefficients for each pair of residues in my protein, and also, similarly to what I was explaining in Seti's paper, we need the distance matrix that will tell me each pair of residues, which is the mean distance of these pairs of residues along the MD simulation that we have performed. So for running shortest path map, we need two matrices, the correlation matrix and the distance matrix. Now, if we move to the next slide, here I put the logic behind the protocol. So I already explained it, but I will explain it again. And I will try to highlight here how this approach differs from the other approaches that I have been talking about. Okay, so the first step is that we assign one node to each C alpha residue. Okay, so we apply graph theory. So we start to construct the graph, and we assign one node to each residue. Then we look at the distance matrix and we draw a line between the different nodes if the distance between, for example, C alpha of residue Y and residue J is smaller than 6 angstroms along the MD simulation. If that is the case, then we draw a line. If that is not the case, then we don't draw a line between these two residues. And then the edge that connects these two residues will be weighted, and will be weighted according to the correlation value. So remember, if they are highly correlated, then we'll have shorter distances, shorter path lengths. If they are non-correlated, then we'll have very long length of these very long lines, let's say. And here, with that, you construct the first graph. So if we go to the next slide, well, it's I did manually because it was faster. But this is the main idea, as I was saying. So here you have an example, for example. So basically, we will draw a line between this pair of residues if the mean distance, in our case, is less than 6 angstroms along the MD simulation. The mean distance, is less than 6 along the MD simulation time. As I said, if there is, and then the line, the length of this line will be related to the logarithm of the correlation. So if they are highly correlated, the length will be will be very short, or very long if they are not correlated. And you get something that looks like this, as the ones represented. Okay, if you go to the next slide, now I will try to explain how we are going to compute these shortest path maps. And here is what is different from what I have explained in the other studies. Okay, so imagine that we have this graph that is displayed in this. It looks like two epoch sides, no? Like these triangular rings. Okay, so we have this is a protein composed by 5 residues. And we have, these different residues connected through these different lines, and you have in blue the value of the length of the path of the that connects the different nodes. So the protocol, the algorithm starts by computing the shortest path maps for residue 1, and we will do that from going from 1 till the end of the protein. So in this case, residue 5. So we'll start and we say, okay, from 1 to 5. First, I want to go from 1 to 2. If I want to go from 1 to 2, I will use the edge 1, 2. shown here in highlight, well, marked with with orange. If I want to go from 1 to 3, what is the shortest path? Now I see that this is wrong. Anyway, then I'll say, okay, from 1 to 3, it's I need to go from 1 to 2 and to 2 to 3. This is wrong. Here I put that 1 to 3. Anyway, then if I want to go from 1 to 4, what is the shortest path map? Well, it's from 1 to 2. From 2 to 3 and 3 to 4. Okay, so these are the edges that I will be using. If I want to go from 1 to 5, I will use what? From 1 to 2, to 2 to 3, and 3 to 5, because it's shorter. 1.5 is smaller than 2 plus 1, and that is 3.
Silvia, one question.
Yes.
So, in order to get it clear,
yes,
you are saying that for going from 1 to 3 is shorter going 1, 2, and then 2, 3, because adding the distance is shorter than 1
4.
to 3.
Yeah.
Okay, and for this reason it's wrong.
Yes.
Okay.
Yeah, sorry. Yeah, I did it quite fast, and yeah. So the idea is to look at the sum of the lengths and see which sum is smaller. Yeah.
Perfect, thanks.
Then we'll do that for the same now, starting from position 2. So from 2 to 3, it's 2, 3. From 2 to 4, 2, 3, 3, 4. 2, 5, 2, 3, 3, 5. Yeah? And you do this all the way till the end. Okay. When you do this analysis, then you start the counting, which is the lower part of the slide. And you say, okay, how many times I have used the edge 1, 2 for in each of the cases. So in one, here you have the summing. So 3, 1, 2, 1. So you see how the different paths different edges have been used to go from the first position to the last position of the protein. And if you go to the next slide, then you can sum, and we see that the edge that has been used the highest number of times is the edge 2, 3, and the max weight of this edge is 5. So it has been used 5 times. I don't know what I'm saying. 5 times. Okay. So with that, then we assign some weights to the different paths, to the different edges. And what we have is that from 1 to 2, so we have that the maximum value is 5. So we take the sum of the different edges and we divide it by the maximum value, which is 5. And we get the weights that are shown in here. So we have that, for example, H12 has a weight of 0.6. However, the H that has the maximum value, of course, has a value of 1. Yeah. And there are some other less used edges that have a value smaller, like for instance 0.2. In the program, what we do is that we only, in the script, what we do is that we only represent those edges that have a weight higher than 0.3. Okay. Only this. Are you here? I mean, is it working fine? Because I'm moving location.
Yeah, I think. Well, for me, it is working fine.
Okay. Yeah. Otherwise, you will hear Paul. Yeah. So what I was saying. So basically, then you have the weights for the different edges, and for visualization purposes, only those that have a weight higher than 0.3 are shown. And now you can ask me, why 0.3? Well, I mean, this is just a threshold, so this can be changed, but I put 0.3. Okay. So you can basically test and try different values. It depends on the, but basically it's because if you, I mean, all the paths this could be removed, but then you'll have many more edges shown in the SPM. So that means that as we apply this threshold of 0.3, the ones that are squared with the blue box, that is 1, 2, 2, 3, 3, 4, and 3, 5, are the ones that are going to be represented. And if you go to the next slide, so that means that by applying this methodology, the original graph that was constructed based or similarly to other strategies, that was originally proposed by SETI, this original graph has been reduced into this SPM, the shortest path map that we compute with the Dynacom. And what you see, what is the difference between these two graphs? Well, first, not all the edges are shown because we have applied this threshold. First important thing. Second important thing, in the original graph, the lines were longer or shorter depending on the correlation value. In the Dynacom, the lines are not shorter or longer depending on the correlation value. Here we focus on the width of the different lines, and the width of the different lines is related to the weights of the edges that come from this counting of how many times we have used that edge for going from one position to the other. Yeah. So basically, as edge 2,3 was the one that was mostly used, is the one that has a much stronger, also a larger width. And the other ones have a smaller, although all of them 0.6. And the ones that had 0.2 are not shown. Yeah. So that's the main idea and the main difference. I hope it's clear. So at this point, if it's and of course, this SPM, I haven't put here the examples where we have applied them because you already know them. But yeah, so you know that the first paper where we applied is in the retroaldolase, that Mark and Adria realized that, well, by applying this SPM, it matched the directed evolution positions, but also this has been applied in MAON, for example, or more recently in tryptophan synthase. But I didn't put the examples. Now, in the next slide, I put different strategies to try to run this script, if you are interested, or this program in Galatea. And mostly, well, and also I need to say that there have been some variations to this original SPM, but I'm not going to also talk about them either because mostly we are tests, and we are mostly validating them. So there are two different ways of running this Dynacom. One is directly in Galatea. In Galatea, there's a folder in My Home where Dynacom is located, so you can call to this, so you can use this Dynacom. And the other one is by using a notebook. So now I'm going to show you the two different options. First option is if you use Galatea cluster, which is easier because you don't need to install anything in your computer, for example. Everything is installed in Galatea. You need to first use CPP track to generate these two matrices, the distance matrix and the correlations matrix. And here there is an example of one CPP track input file for computing both the distance and the correlation. The important key point here is that remember that we are looking at how the position of every residue has been changed along the MD simulation with respect to a reference. So it's very important that the trajectory is properly aligned. We have seen that there are some problems with sometimes, depending on the system, if it's complicated, if it's a dimer, it's sometimes we have had some problems with CPP track doing this alignment. So in this case, you can use VMD, for example, to ensure that it's properly aligned. Or if you use a notebook, then this is solved with mdtrag. Okay, so first step is to run cpptrag to compute the distance and the correlation matrix from the MD trajectory that you have. And you say that you use as reference the C alpha, but you can we have also been testing other options like C beta, or yeah, you can use different strategies. Next slide is that where the SPM is, the Dynacom is located in Galatea. For that, you need to export the path because this was developed a few years ago, so it's Python 2.7. So you need to export the correct path, and then you can execute this Dynacom. And when you do this Python and this path, you'll get the information on how it works. Basically, you put Python, the name of the executable, then minus MD, you specify the distance matrix, minus MC, the correlations matrix, and then minus name. And name, here you should put the name of your system that will be used for generating the outputs. And then you have minus com, and this com is related to the community, finding the community structures that I was explaining in the papers. So I also use use, and these different methods are already programmed. So I imported these different algorithms, and you can also do community analysis with this Dynacom. Although I was a little bit disappointed because depending on the community algorithm that you use, HBetweenness is the Girvan-Newman that I was talking about, but there are also others like FastGreedy or WallTrap. Depending on that, you'll get really completely different community structure. So I did not develop this further. Okay, and if you do that, then this generates multiple files. And of course, you'll get files for showing the communities. You can also do if you want, but we will also get files for showing the shortest, the SPM. And this will provide very important, different PNGs, so images of the graphs that you can use. But I think what is most relevant is to apply the graph into the protein 3D structure. And for that, there is a script for PyMol that is always called like the same, PyMol, shortest path, and then the name that you provide. Also, you can look at the output file. I think if you go to the next slide, yes. So the output file has like the information about the different ages and the paths of the different, the weights, of the different ages. These weights are multiplied by 10, okay, for visualization purposes in PyMol. Otherwise, they were so tiny that you cannot see them. And okay, so that's in here. You also have the image of the graph. And if you go to the next slide, then to show the shortest path map on the protein, basically you open PyMol, you open the PDB of the structure, and you go to the path where you have this PyMol shortest path, and you do the add PyMol shortest path, and it will be shown on screen. Okay, and that's it. So then you have the shortest path map, and you can start analyzing and see whether, which positions are predicted to have an important role in the conformational dynamics of the enzyme, and so this could be proposed to for further mutagenesis. And the cool part is that we are not only selecting, or we are not only identifying active site positions, but also distal mutations. So that might be important. And of course, now you know that we are applying this tool to several enzymes to try to see how powerful the shortest path map is. Option 2 is through Jupyter Notebook. And I put the Jupyter Notebook in Galatea, also in my home, in my bin folder in Galatea. And there's a folder that I called, example Dynacom notebook, where you can find this notebook. So you can download it, and if you want to try with Jupyter Notebook, you can also try. The drawback, let's say, to use the Jupyter notebook, if you want to use it in your computer, is that you need to install iGraph. So that's the library that I use for computing the graphs. And also you need to install Cairo, as you see in the first line. So import Cairo, import iGraph. And unfortunately, I had many problems to install Cairo in my Mac. But in Linux, everything is smoother and nicer. So if you are using a Linux, it will be fine. Yeah, and Cairo is well, in principle, you don't need Cairo, but Cairo will do the plots of the graphs. And so if you want to save the graph, you need to install Cairo. Well, so the first part of the notebook is just to import some libraries. Second is there are some built-in functions that I always load, so no problem. Next slide is where you have the details of where the different options should be typed. So first you put the path where you have the files. This has to be changed, of course, to your path. Then you have the topology. So this is a PDB of the protein that you have done the MD. And then you have the file name of the trajectory that should be a netcdf file. Then you load the trajectory. Then you load the topology. And then here in the last 3 lines, you align with mdtrack the trajectory, taking into account the topology file that you have specified. So in this case, you ensure that all snapshots along the MD are properly aligned with respect to the reference. And you save a new trajectory called align, mdtrack align. Oh, wow. Now it's 1 second.
Yeah, I'm using this for the record. Lorenzo said that Cairo can be easily installed using Mac ports in Mac, so thanks, Lorenzo.
One second, please. Yeah. I'm with Paul now. Well, we can, if he doesn't complain, I can keep talking. So then when you execute this will align the trajectory. And then in the next part, you will load the trajectory that is aligned. Okay. If you go to the next slide, then you'll have computed the distance matrix and the correlation matrix, which is the table dist and the table core. Okay, so with this, instead of using CPP track to compute the distance and the correlation matrix, we use we do it directly on the notebook, and then you specify a figure name, and then below is where the algorithm starts. Okay, is where the algorithm starts. And here you put the distance that is 6 angstroms. So if you want to use, instead of 6 angstroms, another distance, you can change this value in here. If you go to the next slide, then you see how the graph is constructed. Yeah, and this is basically this is iGraph info. So in this iGraph info, well, this is, you don't need to worry that much, but basically in this part, you will get the initial graph that I was talking about plotted. So if you go to the next slide, in this is tryptophan synthase. So that is the initial graph after considering the distance and the correlation matrices. So here you have the lengths of the different paths. The lengths that connect the different residues are directly related to the correlation values. Okay, so and that's the basis for, if you want to do the community analysis, this is the graph that will be used for running the community analysis. Or if you want to do the shortest path map, then that is the starting point. But it's good because you can have a look at how the initial graph looks like. Also, one thing that I need to say is that if you are using the Jupyter notebook, do not trust the images that are displayed on the notebook. okay, because I realize that it has a bug, or at least in my version it has a bug, and the image that is displayed is not properly displayed. So the one that is good is the one that is saved as PDF, and that's the one that you need to look at. Anyway, it was just a minor point. So next is to start the calculation of the shortest path map, as I was explaining before. And if you go to the next one, you have all the different the different force. And you go to the next one, you'll see one that is optional. In this case, I use the tryptophan synthase example. So here with Miguel Angel, we were defining some important parts of the enzyme for visualization purposes. This is totally optional. So if you don't want to use it, do not use it. Okay. And next, then you have the part related to the iGraph, to the graph construction of the SPM. And in this case, if you go to the next one, you see first the SPM printed on top of the original path, or of the original graph. So you see how the SPM looks like by taking into account all, on that original one. Yeah, so many of the connections are now not displayed because of the threshold that we applied. If you go to the next slide, then it will show the part related to iGraph for the construction of the final shortest path, which is in the next slide, which is the SPM graph. Okay, so here, and there are some positions colored. Here they had the same, I don't remember the meaning, but some of them were important, so we were like coloring the ones that were important to see whether we were predicting the Arnold's mutations or not. Okay, if you go to the next slide, then it's another version of the shortest path map. In this case, is the shortest path map where we put the value of the correlation of the different two residues. But of course, take into account that this value of the correlation will not be, of course, it's related to the shortest, to the edge, to the width of the edge, but it's not like 100% equivalent, let's say. And next slide is to generate the output for PyMol. So if you execute this option, then you'll have the PyMol script that then, if you go to the next slide, similarly as I have explained, this can be applied in the protein structure, and you get the SPM on PyMol to have a look at. And that's pretty much it. So I think, that's the end of the tutorial. Sorry, I think I'll talk a lot, but I don't know if there are questions.
Yeah, I have one question.
Mm-hmm.
Because of the weighting of the